Okay, this is your active transport, which pushes ions against its osmotic gradient. And to do that, it requires energy. But this specific example, we're covering the sodium-potassium pump, which helps maintain osmotic equilibrium and membrane potential. Now, you should know that this is the outside of the extracellular membrane, and this is the inside. Now, this square is your potassium, and you can see by the less on the outside, more on the inside, it is moving in. And your circle is your sodium, and it is moving, see, more on the outside, less on the inside, it is moving out. Okay? And in order to move it against its osmotic gradient, it needs to be powered by a phosphate, and that phosphate comes from ATP. Your ATP will deposit a phosphate here, and it will become ADP. Now, this addition of the phosphate molecule will change the shape of the active transport protein, allowing the sodium on the inside to move in. Say three of them will move in, and they will bind to the surface, and they will be pushed out against their gradient. Now, after these are pushed out, the shape of the active transport changes, and this allows the potassium to move from the outside inside. It will bind to the surface just like the sodium ions did, and it will be pushed inside the cell. When this is done, and the phosphate has finished its job, it will leave, returning this active transport to its original shape. It will return to its original shape, and the phosphate will meet the ADP in the mitochondria, and it will form a new ATP. Now, the importance of this specific pump is that it is used to send signals as it is pushing charged ions against its gradient. Now, active transports are different from passive transports because they do require energy in the form of ATP to function, because it's pushing, instead of pushing, flowing along with the gradient, it's moving against it. So that's really the important part. It's against, requires its ATP, and this is just a specific example that we've drawn.